So the best way to get these values the quickest, rather than typing this in 6 different times, would be to plot the function, or to plug in the function sine of x divided by x. What mode should we be in? Radians, which I have to check because I'm doing stuff with algebra 2 right now and we're going back and forth. So radians. And then a window, you could just go 0 to 2, and then min and max will go, I don't know, negative 10 to 10 to start and see what happens. Let me do something different. I'm going to do negative 2 pi to 2 pi. Okay, so to fill in our table of values, second trace will allow you to just pick which value you want to look for, negative 0.1. When you plug that in, we get 0.998. 998. Do it again, second trace value. We want an x value negative 0.01. That's 0.99998. 0.99998. So is that getting bigger or smaller? Bigger. Second trace value negative 0.001. And then we have 0.9999998. Oh gosh, 1, 2, 3, 4, 5, 6. 6 of them. Also getting bigger. Seems to be approaching what? Because 0 is going to be right in there. Seems to be getting closer to 1. Infinitely close to 1. On the upper side of things, if I plug in positive 0.1, oops, 0.1, I have 0.998. I'll save you the time. When I plug in 0.01, it's also going to give me 0.99998. And when I plug in 0.001, I'll get the same thing. Okay, so when we come from this direction, we're approaching 1. When we come from this direction, we are also approaching 1. So the limit as x approaches 0 of this function equals 1. Right at 0, what would the table of value say? Liam? Undefined. Because if you plug in 0, you're going to get the sine of 0 over 0, which is 0 over 0, which anything divided by 0 we can't do. So you actually don't have a point at 0. And let's see what happens. You're not going to probably see it on this graph, but if I zoom in, change my window, negative 1 to 1, and 0 to 2. There it is. So you're not going to see it there, but there's a hole there in your graph. Okay? The graph has the intention as you come from the left of hitting 1, has that same intention as you come from the right of hitting that y value of 1, but it doesn't actually hit it because there's a hole there. The graph is undefined there. Does that make sense? Okay? So the function value is not 1, but the limit is 1. Stephen. Some of it will be. So here's a little bit of notation here. This says the limit as x approaches 0 with a little superscript of a negative sign means you're approaching 0 from the left. And that was 1. That was when we were coming from the negative side of things. We were approaching 1. And this superscript of a plus means from the right. And that was also 1. two match, does the overall limit exist? So we'll talk about the limit from the left, we'll talk about the limit from the right, and then we'll talk about the overall limit as we approach that number of the entire function, and that will only exist if these are the same. Okay? So sketch a graph of the function to confirm your results. I don't really remember what's happening over here, but I know this is kind of approaching 1, but there's a hole there. And this is, we'll just put 1 so we know the value that we're at. Okay? So then we talk more about what I've already questioned you about. In the function, f of 0 equals 0 over 0, which is undefined. But the limit as x approaches 0, we now know is 1. So just really pointing out that even though the function value doesn't exist, the limit still can. Okie doke? Okay. Here is a new example, a function that's a little more familiar to us, 3x squared. So we want to see what the limit is as this graph is approaching 4. So we're going to plug in things coming from below 4, coming from the left, getting closer and closer to 4. And then we're going to plug in things coming from the right. That's supposed to say 4.1. Coming from the right, coming from above 4, kind of getting closer and closer to 4, coming from the positive side of things. So again, the best way, rather than having to plug this in 1,000 times, is to just, oh my word, delete, delete, 2. Okay. So I'll do a zoom 6, a standard window, and then I'll just do second trace. I'll plug in 3.9, I'll plug in 3.99. 3.9 gives us 45.63. Second trace, 3.99 gives us 47.76. And 3.999 gives us 47.98. So when you're coming from the left, what does it seem to be approaching? What'd you say? 48. You know, you really could do like second trace, and I'll do this a lot, value, and I'll plug in 3.9999999 and look at your output, 47.999. It kind of sheds light on what it's getting closer and closer to. On the right-hand side, second trace, value, 4.1, gives us 50.43. Second trace value, plug in a 4.01, gives us 48.24. And second trace, 4.001, gives us 48.02. So you kind of want to look at the chart in two different pieces. What is this getting closer to? And we think 48. As you're coming from the left. So that would be the limit as x approaches 4 coming from the left of this function. We'll just say f of x rather than writing 3x squared, doesn't matter. So the limit of this function as you approach 4 from the left, the function value is approaching 48. And then you look at it coming from the right. What's happening to our function value? We start at 50.43, and then we drop to 48.24, and then we drop to 48.02. What is it approaching as you come from the right-hand side? Also appears to be 48. And again, I could do second trace and find a value at 4.000 and get kind of infinitely close to actually 4, and you get 48.002. So on both sides, regardless of which side you're approaching from, we are approaching 48 and they match. So the limit as x approaches 4 overall of this function is 48. You'll find out that you don't, but we're just kind of exploring the meaning of the limit. So what he's saying is, in this one, that's what 4 would have been. If you plugged in 4, you would have gotten 48. Okay, but in some things, you can't just plug in. So you have to understand this concept. In some things, I hate to tell you, you will plug in the number, but that's not the answer. Okay? So we'll look at examples where you could plug in the number that you're approaching, and the answer it gives you is not going to be the same as what the limit is when you approach that number. So there's a lot of different scenarios to think about, but this is a case where, of course, that is the answer. If you obviously look at this graph, if I change my window and go from -5 to 5, and then have my y go from 0 to 100. Here's 1, 2, 3, 4. Here's the point that we're approaching graphically. 1, 2, 3, 4. On our graph, we're right about here. Obviously, as you approach from the left, you're getting closer to that 48 number. As you approach from the right, you're getting closer to that 48 number. And there is a point there. There's not a hole on this case like there was the last one. So that's why your function value matches your limit here. Use the graph of f of x shown to find this limit. So we're just kind of sketching what I just had. 1, 2, 3, 4, we'll say is right here, and that's at 48. So this is illustrating what we were lacking on the other side, where the limit and the function value did not exist, or did not match. Here, the limit is 48, the function value is 48. Okay, and what we're going to get to, and I'll just talk about it now because this is what's happening, is the difference between a continuous function and a discontinuous function. This function is continuous at 4 because the limit is the same thing as the function value, so you can draw a continuation of your graph without having to pick up your pencil off the paper. Versus on this side, the limit exists, but the function value didn't really plug that hole, and so it's a discontinuous function because you have a discontinuity or a break in the function where you have to pick your pencil up off the paper and you have to start on the other side. So it seems really easy and obvious, and it is in a lot of ways, but there are so many quirky examples that we'll explore that won't make it seem so simple and straightforward. Okay? And here is one of them. Piecewise functions kind of throw us for a loop. We have to look at them more closely. So graph this function, and we're going to use the sketch of our graph to find this limit as x approaches 3. So this is a piecewise function where it's essentially a linear function, 2x minus 4, everywhere except for right at 3. So 2x minus 4 would have a y-intercept of -4 and a slope of 2. So you'd go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And if it wasn't a piecewise function, that would be your graph. But this linear function does not apply at the point where x is 3, which is right here. So that's actually an open circle. That's a hole in our line. And then, just so this function actually exists at 3, there is a point at 3, negative 5. So here's kind of a piecewise function with a hole. So the limit of our function as we approach 3, as you approach this x value of 3 from the left, what is your y value approaching? Nope. 2. How'd you get that, Adam? From here. He went up 2 over 1. Right. So that's what it would have been, but since there's a hole, it's actually not. But the limit as you approach from the left, so let's do this. Limit as x approaches 3 from the left of this function is 2. How would you get that if you didn't draw the graph? Right. Essentially your graph is this line. Yes, there's a hole right at 3, but that doesn't mean you can't still plug 3 in and get 6 minus 4 to find out that had they not made this so there was a hole, that's where that point would have been. Would have been at 2. And then obviously the same is true if you're approaching that from the right. Your limit is also 2. So the overall limit is 2 because those match. Yet the function value, just f of 3, does not equal 2. F of 3 equals what? Negative 5. Now because the limit and the function value don't match, it's not continuous. And obviously the visual of that makes that really, really clear. But we're going to get to lots of stuff, guys, that we don't know what the graph looks like. And you're not going to have a calculator to plug it in. So you have to understand kind of these more algebraic approaches and understand the definition, because it's not going to always be as easy as just, hey, let's just look at the picture, because you're not going to have the picture. There are going to be plenty of graphs we run into that you can sketch the picture of, and you know enough about the features of those functions and what their graphs look like that you will be able to resort to the graph, but not always. And in those instances, you have to understand these definitions. What needs to happen for the limit to exist, what needs to happen for it to be a continuous function, which this one is not. The limit exists, but the function value doesn't match it. So we've got a hole that's kind of, the point is plotted elsewhere, and so we have a discontinuity. Does this make sense? Was that easy? Okay. So I think maybe I'll just throw the book up and let you